this is the symbol of Zener diode. So it has quite similar symbol, quite similar with the normal diode, except at the cathode here. At the cathode of Zener diode, it has the shape of Z. Okay, the shape of alphabet Z or Z. So referring to the Zener. Okay, so usually the anode in normal diode, the anode is associated with the positive terminal, cathode is negative terminal. But since the Zener diode operate at reverse bias, so it operates at reverse bias operation. So we apply positive voltage at cathode and negative voltage at anode. So by applying at reverse bias operation, so the current will flow from cathode to anode. So note the current you need to note to take note on the current direction. So it's from cathode to anode. This is direction of the Zener current IZ. Okay, so this slide show the equivalent model for the Zener diode. So here again, the Zener diode operate at reverse bias, So operation of Zener diode, we divided into two states, off state and on state. Okay, the off state is where the current is zero. So the current zero is when the supply voltage is lower than Vz. Okay, and then the current is on when V supply voltage is higher than Vz. So at the off state where Vs is lower than Vz, so the Zener diode can be replaced by the open circuit. Okay, here the Vs is larger than 0. This is Vs is 0 because this is if Vs is lower than 0, this is actually referring to the forward bias. Okay, because we are the definition of Vs is this one. This is Vs. Okay, so the on state at the on state, the Zener diode can be replaced by the battery. So the battery with a voltage of Vz. So this is quite similar to the diode, the normal diode. At on state, the diode is replaced by the battery, and the battery, the value of battery equal to the barrier potential or the knee voltage. But here for Zener diode is equal to the knee voltage of Zener, or we call it Vz. Okay, so the previous slide actually show the ideal model. In more practical model, we need to consider the internal resistance inside the Zener diode. So this is ZZ. ZZ is a this is average resistance at Zener on operation. So this is on operation. This is where the Zener on. Okay, if you see this current, this is the current. The magnitude of current increase in linear fashion, so we can get the R average AC resistance, and then the average AC resistance is equal to ZZ. This is delta Vz over delta Iz. So in the practical model, we need to consider the Vz. So when we consider the Vz, you can see that the Vz here, the actual Vz across the Zener diode is not a fixed value. So there will be a small fluctuation of the total Vz. This is total Vz. Let's say I put it Vz prime here. This is Vz. So this is Vz prime. So Vz prime is equal to Vz plus Iz Zz. Okay, you can see here Vz prime is not equal to Vz. You need to add the voltage drop at the Zz. Okay, the constant voltage drop is represented by a DC voltage source, normally external R. It is much larger than the Zz, therefore ideal model is usually used. So usually we only use the ideal model. Okay. This is the one that we'll use for analysis. But keep in mind that in actual application of Zener, the voltage across the Zener will not be a fixed value. There will be a change in the voltage due to the voltage drop across the internal resistance. Okay, next we have the temperature coefficient, okay, or TC. TC specifies the percent change in Zener voltage for each degree centigrade change in temperature. So the value of Zener voltage or Vz is also influenced by the temperature, the ambient temperature. So as what I think you have learned in the previous week, the normal diode also the operation of normal diode is also affected by the temperature. So that's why we have the temperature coefficient. So it's defined by TC. So when we have the TC, actually we can get how much the changes in Zener diode. So delta Vz is the changes of the Zener diode. So Vz is the Zener voltage. Vz is Zener voltage at the reference point. This is Zener voltage at reference point. And this is the temperature change. Okay, so positive TC means that Vz increase with an increase in temperature. So for example, we have 8.2 volt Zener diode, and it has a positive temperature coefficient of 0.05% per degree Celsius. What is Vz at 60 degrees Celsius? So the Vz of reference, let's say reference here is 8.2 volt. So usually this is the measured Zener voltage at 25 degrees Celsius. So the solution is delta Vz. This is the changes of the Zener voltage is equal to Vz reference. This is 8.2 times the TC is a temperature coefficient. Is 0.05%, so 0.0005, and then times the difference of the temperature, 60 to 25. So we get the delta Vz is 144 millivolt. So the Vz at 60 degrees Celsius is the reference plus the delta. So 8.2 plus 144 milli. So we get 8.34 volt. So the next related parameter of the Zener diode is power dissipation. So the general equation for the power is P equal to IV. So PD refers to the power dissipation. So Zener diode are specified to operate at maximum power called the maximum DC power dissipation, or PD max. So when we operate at reverse bias, the current will above the Zener voltage, the current will start to flow rapidly. So the increment of the rapid increment of current will lead to the device damage. Will damage the device. So we need to limit the maximum current here, and then the maximum current relate to the maximum power dissipation. So PD max. So usually the PD max also equal to Vz Iz max. So PD max will relate to the Iz max. the maximum current across the diode. Okay, and then we have the power derating. PD max of Zener diode is typically specified for temperature at or below a certain value. Above the specified temperature, the PD max is reduced according to the derating factor. Derating factor is expressed by milliwatt per centimeter per degree Celsius. So derating factor is actually referring to the how much the difference, the derating factor, how much the changes in the maximum power when the temperature decrease. So that's why we get here PD derated equal to PD max minus the derating factor times delta F. So this is, in this term, we should get how much the changes due to the temperature changes. So PD derated is the reduced PD max. So PD max is a maximum power dissipation at the reference temperature. At the reference temperature, PD derated is at specific temperature. For example, a certain Zener diode has PD max equal to 400 milliwatt at 50 degrees Celsius and a derating factor of 3.2 milliwatt over degree Celsius. Determine PD max the Zener can dissipate at a temperature of 60. Okay, the solution is using the previous slide equation. PD derated is equal to PD max at reference minus the how much the difference of the power maximum power. So you have here the PD max is at the reference point, which is at 50 degrees Celsius, 400 milliwatt. So this is the derating factor times delta T, temperature difference between 90 to 50, and then lastly we get 272 milliwatt. So you can see here, when the temperature is high, the P max is become lower. So it's easy for, if the temperature is high, it's easy for the Zener diode to be broken down because the P max is lower. Okay, this is taken some portion or some part taken from the data sheet of a Zener diode. Okay, this is Zener diode for IN4728, IN4764 series 1 watt Zener diode. Okay, you can see here we have the leakage current. Okay, this is the YSAG test current, YSAG T. Okay, and then this is the nominal Zener voltage, YSAG at YSAG T. Okay, IR for value of VR is must be lower than VNI or VZAG. Sometimes manufacturer will give YSAG max rather than PD max. So this is I have explained regarding this in previous slide. So some data sheet they will give the PD max, the maximum power dissipation, or if PD max is not given, usually they will give YSAG max because here VZAG is fixed. So if PD max change, YSAG max also change.